Imagine a world where electricity flows forever without losing even a single drop of energy. Or where a liquid climbs up the walls of its container, defying gravity itself. These are not scenes from science fiction, they're the realities of two of physics' most astonishing phenomena, superconductivity and superfluidity. Welcome to the Learning Studio, and in today's episode from our physics playlist, we'll journey into a realm where matter behaves in ways that seem almost magical, yet are rooted in the deepest laws of quantum physics. You can explore the entire physics playlist by clicking the link below in the description. This topic is part of our section Matter, Materials, and the Rise of Technology, where we explore how the strange behaviors of matter are shaping the technologies of the future. When ordinary matter becomes extraordinary. Under normal conditions, every material has resistance, whether it's copper, aluminium, or even gold. When electricity flows through these materials, some energy is always lost as heat. That's why power lines warm up, and why your laptop sometimes overheats. But in 1911, physicist Heike Kamerlingh made a discovery that changed physics forever. While cooling mercury to extremely low temperatures, near absolute zero, he noticed something incredible. Its electrical resistance suddenly dropped to zero. Electric current could now flow indefinitely without losing energy. He had discovered superconductivity. The quantum secret behind superconductivity. At first, scientists couldn't explain how this was possible. But later, quantum mechanics provided the key. Inside a superconductor, electrons don't behave as individual particles anymore. Instead, they pair up into what we call Cooper pairs, tiny quantum partnerships that move through the material in perfect harmony, without colliding with atoms or losing energy. It's like a perfectly choreographed dance, where every step is in sync. This collective motion gives rise to one of nature's most astonishing effects, zero resistance and perfect diamagnetism, meaning superconductors can even repel magnetic fields. That's why we can make levitating trains, the famous maglev trains, that glide without friction using superconducting magnets. But the real revolution is yet to come. Superconductivity and the future of technology. Superconductors have the potential to completely redefine energy in technology. In power systems, they could allow electricity to travel across continents with no energy loss. In medical imaging, superconducting magnets make MRI machines possible. In particle accelerators, they guide beams at nearly the speed of light. And in quantum computing, superconducting circuits are used to build qubits, the building blocks of quantum processors. Researchers are also searching for high-temperature superconductors, materials that can exhibit zero resistance even at temperatures much higher than near absolute zero. Once achieved, they could revolutionize global energy grids, transportation, and AI hardware, making computation faster and greener than ever before. Superfluidity, when liquids defy logic. Around the same time superconductivity was discovered, another strange quantum phenomenon emerged, superfluidity. In 1937, scientists found that liquid helium, when cooled below a critical temperature, began to behave in impossible ways. It could flow endlessly without friction, climb up the sides of containers, and even escape through microscopic cracks. In a superfluid, atoms move as one, a single quantum wave, with zero viscosity. There's no resistance, no turbulence, and no energy loss. It's as if the entire liquid becomes a single, perfectly coordinated entity. Just like in superconductors, quantum coherence lies at the heart of this phenomenon. And in both cases, what we see is matter entering a macroscopic quantum state, where quantum rules no longer belong just to atoms, but to entire materials. Where quantum physics meets real-world innovation. Superconductivity and superfluidity are not just exotic lab curiosities, they are the blueprint for the next generation of technologies. Quantum computers use superconducting circuits to process information with minimal energy loss. Fusion reactors rely on superconducting magnets to confine plasma and create sustainable energy. AI hardware may soon integrate superconducting logic, reducing computation time and power use. And space exploration could benefit from superfluid cooling systems operating in extreme environments. Even in fundamental physics, studying these states helps scientists understand the deeper link between quantum mechanics, thermodynamics, and information theory. They reveal how matter can organize itself into new states, states that might one day lead to room temperature superconductors or even new forms of quantum matter we haven't yet imagined. The quantum frontier of matter. What makes superconductivity and superfluidity so fascinating is that they blur the line between the classical and the quantum worlds. They show us that the universe still holds surprises, hidden behaviors that only emerge when we look deep enough and cool things down far enough. They remind us that even the coldest moments in physics can ignite the warmest sparks of discovery. This is the Learning Studio, and this was our episode on superconductivity and superfluidity. If you enjoyed uncovering how matter can defy resistance and flow infinitely, make sure to subscribe, like, and check out the physics playlist linked below. In our next episode, we'll explore condensed matter physics and emergent phenomena, where complexity itself becomes a new law of nature. Because in physics, when we go deep enough into the cold and the small, we often find the hottest ideas about the future.